In this podcast, we're going to be looking at the graphs of exponential functions and log functions first, and then depending on how long that takes us, we may look at some other things as well. All right, so here, and this is in the notes, and it's some basic things about the graph of exponential, and this is exponential growth. Okay? So exponential growth is going to increase as, the function is going to increase as x increases. And so we'll have a growth function anytime our base is greater than 1. Okay? So like, for instance, f of x equals 2 to the x or 3 to the x or anything larger than 1. Our domain is all real numbers. You can plug in anything for the exponent. Our range is going to be all positive numbers unless our function's been shifted. If we subtract something from our function or add something to it, we could change it up a little bit. And we'll take a look at some graphs that have been translated. But if it's just a plain old exponential function, y equals a to the x, or a is some number greater than 1, our range is going to be all positive numbers. And that's because if we raise a base to a power, we're going to get a positive number. We will have a y-intercept at 0, 1. And that's because if you raise anything, oops, come on, pen, anything to the 0 power, well, with the exception of 0, you're going to get 1. But that's okay because our base will never be 0. So if you raise 2 to the 0 power, it's 1. If you raise e to the 0 power, it's 1, etc. So all of our functions, if all of our exponential growth and decay functions, if they haven't been translated, we'll go through the point 0, 1. If it's growth, it's going to be increasing. And then the x-axis is going to be a horizontal asymptote. Excuse me, horizontal asymptote. So that means as your function, as x goes to negative infinity, the graph is going to go to 0. So on this side, we're just going to get larger and larger, so we're increasing. So on this side, as f of x will go to infinity as x goes to infinity. But on the other side, because of the horizontal asymptote, f of x goes to 0 as x goes to negative infinity. So that's a horizontal asymptote as we're going to the negative side. And it is a continuous function. Let's compare that to exponential decay. Looks a lot like exponential growth, it's just going the other way. And here, this is the graph of y equals a to the negative x. So if we have a to the negative x, we know that our base is going to be the reciprocal. So for instance, this would be y equals 1 over a to the x. Okay? So our base isn't greater than 1 because it's in the denominator. The base altogether is actually between 0 and 1. So I'm just going to put base. Okay. So for instance, if a were 2, and we had 2 to the negative x power, that would be y equals 1 over 2 to the x. So it's in the denominator, so this is going to be exponential decay. Same domain, same range, same y-intercept. What's different is instead of increasing, we're going to be decreasing. We're decaying. Okay? So that's going to change our end behavior. So now it's going to be just the opposite of what we had for exponential growth. So now f of x will go to 0 as x goes to infinity. And on the other side, f of x will go to infinity as x goes to negative infinity. And then the only way that this value 0 here would change is if we add or subtract something to the function, because then it'll move the whole function up and down. And the same thing over here with growth. If we add or subtract something to our whole function, it's going to change this value here because it'll move the whole graph either up or down. Okay, but we'll take a look at that. right, so let's look at our log functions. Okay? So the log function is the inverse of the exponential function. So on our inverses, everything is reversed. Right? So our x and y values are reversed, for instance. When we have an exponential function, right, so let's just say, here we have 2 to the x, right? So let's say we had f of x equals 2 to the x, right? So the x here is the exponent, and the y, or the f of x, is the result. With our log functions, that's going to be reversed. So now it's the x is not the exponent. It's going to be the result. It's the y that's the exponent. So your x and y values are literally switched. Exponent, there we go. They're literally switched. And that means your domain and range is switched. Okay? So now the domain so on the exponentials, our domain was all real numbers. We could plug in anything for the exponent, but we could only have positive answers. Now your domain is just the positive numbers, because your domain represents the result. And since your exponent is now the range, and the exponent can be anything, your range is all real numbers. So the domain and range are switched. Okay? If our base is greater than 1, we're increasing. So that would be like the one to the left here. This one is increasing. Slowly, but increasing. And if its base is between 0 and 1, our log function will be decreasing. And we can, both the exponential and the log functions can be shifted. I have some of the log functions, and I can show you how those are shifted. And I'll show you the same thing on the exponential functions. And actually, I probably should have grabbed a few more graphs and put that in here. All right, so here we want to figure out which function is represented by the graph below. All right, so we know, so first of all, identify whether this is exponential, whether this is an exponential function, and if so, is this exponential growth or decay. Right, so an exponential function has this characteristic curve. It decreases very quickly, or increases if it's decay, and increases very quickly if it's growth. This is definitely an exponential function. It is not polynomial. Right? It is not one of the shapes we would have for a polynomial function, certainly not linear. It is definitely an exponential function. And now, is this growth or decay? Well, it's decreasing. Right? It's going down. So it's decreasing. Okay? So this is exponential decay. All right, so now let's look at our choices over here. Well, right off the bat, you can see some choices are just very, very wrong, like C here. That's a linear function. Okay, our graph is not a linear function. B here, that's a parabola. Parabola looks like a U. That is not a U. And so this is not, where's my U? I just drew a U and there it goes. So this is not a parabola. Okay? So and then here we have y equals e here, y equals x to the 1/2 power. That's a square root function. X to the 1/2 is the same as the square root of x. So that is not an exponential function. Square root function looks like that. Number one, two that are even exponential, and one of them is growth. 2 to the x, we have a base greater than 1, that is growth. Y equals 1/2 x, that is decay. So we don't even have to match up points here. There's only one that it could possibly be, because there's only one decay function on here. And that is y equals 1/2. 1/2 to the x power. Right? So look carefully at the equations and rule out ones that are the wrong function. And then take a look at which exponential functions do you have left. Is this growth or decay? So here we had one growth, one decay, and that would be the correct answer. All right, so some transformations. Oh, I did put the transformations in. Ah, good. I almost forgot I had done that. So transformations of our exponential functions. Okay? So when we add something, and it doesn't matter what kind of function it is. Our log functions, exponential, when we were graphing square roots, our parabolas when they were in vertex form. We even did it with linear functions. Whenever we add something to the x, it moves our function right and left. Okay? Add to the x, move right and left. Okay? Just remember that. All right? So because x is horizontal, right? It's a long. The x-axis goes right to left. Right? So if you add to x, it's going to move it right and left. So here in blue, we have y equals 2 to the x. That's our base function. And next week, we're going to be graphing these functions. And the best way to graph is, and it helps you understand the functions better, is to graph a base function and translate. And that's actually what I've done here. I have two translations of our base graph. So y equals 2 to the x is the base graph. And we can get that just by graphing some very, very simple points, like 0, 1. So if I raise 2 to the 0 power, I get 1. If I raise 2 to the second power, I get 4. If I raise 2 to the third power, I get 8. Some very basic points are on that blue graph. If I add to the x, and I have a positive number, so in the red there, we have y equals 2 to the x plus 3. Just like all of our other functions, when we add something positive, it moves it to the left. Right? So I'm going to put that up there. Adding to x moves left. Okay? It's going to take a smaller value to get to the same place. Okay. So now if we compare, so here if we compare our points, so we have 0, 1, and then over here I have negative 3, 1. Okay. So same y value. So to graph y equals 2 to the x, I only have to plug in 0 to get to 1. Right? So I have to plug in 0 and I'll get 1 as an answer. If I want 1 as an answer for y equals 2 to the x plus 3, I have to plug in a much smaller number because it's negative 3 plus 3 that would give me 0. Okay? So because I have that plus 3 there, I have 3 additional. I have now, to get to the same y value, I need to plug in a number that's 3 smaller. Okay? So it shifts our whole function to the left. Okay? So when you see a positive added to x, remember it's just like every other function we've done this year. That's the nice thing about these functions. The rules never change. They're all the same. It's going to move it to the left. Okay? And you can see the comparison of all the points there. That's why I matched up the same points. So if I want to get to 8 with y equals 2 to the x, I've got to plug in 3. If I want to get to 8 with y equals 2 to the x plus 3, I only have to plug in 0, 3 smaller. Okay? So the whole function shifts 3 to the left. And the same thing happens, the opposite happens, I should say. The opposite happens if we have a negative. So if we are subtracting, we're going to move to the right, because it's going to take a larger number if we're going to go and subtract something. All right, so now if I want to get to 1, if I want to raise 2 to the x minus 4 power to something and plug in something for x there and get to 1, I've got to plug in a 4. Well, with 2 to the x, I only had to plug in 0. If I want to get to 8, I've got to plug in 7 now instead of just 3. So now I'm going to have to plug in a number that's 4 greater. So horizontal shifts are caused by adding a positive. It will shift it left, or a negative value shifts it right to the exponent. So let's look at some vertical transformations. So our notice here, all we've done is move it left or right. That horizontal asymptote hasn't changed. It's still at 0. We're just moving the graph left and right. Vertical translations. Vertical shifts are caused by adding a positive shifts up or negative value shifts down to the entire function, not the exponent. They change the horizontal asymptote of an exponential function from y equals 0 to y equals the value added to the function. Okay? So now it's not added to the it's not added to x, it's added to the whole function. Got a random f here. He belongs over here. I'll have to fix that later. All right, so here I've got y equals 2 to the x in blue. And we have y equals 2 to the x minus 4 and y equals 2 to the x plus 3. So this time it's not to the x, it's to the whole function. It's not on the exponent. It's a nice big number now, not that little exponent. All right, so y equals 2 to the x has a horizontal asymptote at, oops, I should not have moved that. Oh well, hopefully I haven't moved that too much. Has a horizontal asymptote at y equals 0. Okay? So horizontal asymptote is at y equals 0. Looks like I moved it ever so slightly. I think it's okay then. So y equals 2 to the x plus 3. If we add 3, it shifts the whole function up 3. So now we've changed the horizontal asymptote. We've also changed the end behavior and we've changed the domain. So now over here, as x goes to, so on the blue graph there, it was f of x goes to 0 as x goes to negative infinity. On the red graph, f of x goes to 3 as x goes to negative infinity. And then on the green graph, the one that's been shifted down 4, okay, so now it has a horizontal asymptote at y equals negative 4, f of x goes to negative 4 as x goes to negative infinity. So we've changed the range, we've changed the end behavior, and we've changed the horizontal asymptote if we add something to the whole function. We're going to shift it up and down. Those are the two main transformations that you're going to need to know for the benchmark. And those are the main ones that we'll work with, just really the horizontal and the vertical. So we have, and we will look at reflections as well. It just means you have a negative in front of your whole exponential function. But right now, let's take a look at this particular question. We want to identify which function it is. First thing I notice is the function's been shifted. Which way has it been shifted? Well, the first thing you should notice and should ask yourself on the transformations is, did the horizontal asymptote change? And clearly it has. We are no longer stopping at the x-axis. We can see here by this curve that it looks like we're stopping right here at negative 1. It's trying to get closer and closer to negative 1. So now we have a vertical asymptote at y equals negative 1. Did I just say vertical? Horizontal if I said vertical. Horizontal asymptote at y equals negative 1. Right, so that means that our whole function's been shifted down 1. It means that we have whatever our function is. So f of x equals whatever our base is. Well, you can see they're all 2's. So it has to be a 2 to the something. Maybe there's something added to x, but there definitely has to be a minus 1 because we've shifted the function down. So, and we didn't shift it down a half. Right? We've clearly crossed the halfway mark here. There's about the halfway mark. Clearly have crossed it. So C is not shifted down far enough. D is not shifted at all. It was shifted right and left. That won't change the horizontal asymptote. So now we're left with these two. Okay? So now we have to decide. It's got two things there. Did we shift it right? Did we shift it left besides the down? It's not as easy to see the right and the left part as it is the down, the up and down. All right, so let me put the x in there because we know that's there. So we have to decide, is it shifted to the right or shifted to the left? Well, we know it's shifted down. We know it's shifted down 1. Let's think about our exponential growth function. Whenever we have a key value, that it has to go through. Right? If we raise something to the 0 power, we get 1. Okay? So that point we know is going to, all of our exponential functions, if they're not shifted, is going to go through. So if this were just, I'll graph it on there, y equals 2 to the x. If this was y equals 2 to the x, we'd have 0, 1. We'd have, if we raise 2 to the first power, so this, I'm just graphing here, y is equal to 2 to the x. If we plug in 1 for x, we'd have 2 to the first, and that would be 2. 2 squared would be 4, and 2 cubed, it doesn't fit on my graph anymore. 2 to the negative 1 power would be 1/2, and it'll have an asymptote there at 0. So this graph right here is y equals 2 to the x. So now, that's always a great way, if you're not sure, is to just graph the base function, and then you could figure out, hey, which way did it go? So we know it went down 1. So that we're sure of. Well, which way did it go, right or left? Well, we can see we went to the right. We went to the right. So this point here has gone 1 down and 1 to the right. Which one moves it to the right? Well, it's x minus 1. If you add a negative to x, you move to the right. A, that is the correct answer. Okay. This one's a little bit trickier, but I hope it's making some sense to you. And the more we graph, the better you'll be at this. And actually, these are really nice to graph. Which function represents f of x equals e to the x plus 4? So e to the x has a lot of decimals in it because it's e to the x is a never-ending, never-terminating irrational number. But we don't really have to worry about that because we clearly have 4 different transformations here. So all we really have to figure out is which one did they translate correctly. Right? So if we have f of x equals e to the x plus 4, which way did our graph move? Okay? If we add to the whole function, it moves it up and down. It's positive. Our graph should have moved up 4. Okay? Up 4. And that means we have now a horizontal asymptote at y equals 4. That's the point we're not crossing. Well, this graph here, A and C, have been moved right and left. That's wrong. B was moved down 4, and D is the correct answer. That's the one that moved up 4. So right here is f of x equals e to the x plus 4. So sometimes these are really easy to figure out, especially when we're looking at one translation and it's vertical and they've all moved 4 different ways. All you have to do is identify the one that moved the right direction. So that's D. Oh, I hate when it boxes. There goes my numbers. Okay, so now we're looking at the log functions. Okay, so we see we have no translation here. And, well, how do we know it's log and not exponential? Well, an exponential function, first of all, wouldn't cross the x-axis, and it would look like that. That would be, I should actually have done a different color besides red, green. That one would be an exponential. Okay? That's the shape of an exponential. Not this one here. Right? This one we're growing fast on the x and really slow on the y, and that's because the result grows a lot faster than the exponent. So f of x equals 2 to the x is way wrong. Okay? It would look like the green graph. So that leaves these 3 here. All right, so there's no translations here. Remember on our log graph, on our exponential, we went through the point 0, 1. On the log, we're going to go through the point 1, 0, right? Because the x is the answer, the y is the exponent. You raise to the 0, you get 1. Okay? So we should go through that point there. All right, so now let's take a look at the next value. Okay? Next clear value. Clearly, I'm going through this point here for 1. Okay, so that means I've raised something, some base, so because y is the exponent, I should write exponent here, and 4 is the result. So I'm raising something, I'll just put a box. I'm raising something to the first power, and I'm getting 4. Well, what can you raise to the first power and get 4? Well, of course, 4. So that means my base is 4. So look for clear points. Remember, your x's are your result, and your y's are your exponent. Okay? So look for, you can't, I mean, 1, 0 is not much help because all of the log functions will go through 1, 0. But then continue on. Look for the next clear point. Go along the y and figure out where does the graph cross at y equals 1. And y is 1 when x is 4. And so that means you're raising something to the first and getting this. This is going to end up being your base, because the only way you're going to raise something to the first power and get the same thing is if you're raising that thing to the first power. That made sense. That was an awkward sentence. So that's our answer. If it had been B, we would have had the point 2, 1. And clearly at 2 we're only at a half, which makes sense because 4 to the 1/2 power is 2. And this is base 10, so this would have gone through the point 10, 1. And by 8 we're at 1.5, so that's clearly wrong as well. So C is the correct answer there. So just look very carefully at the points, and I know that you can figure this one out. All right, so transformations. I'm already at 26 minutes on the graphing because this does take a little longer to go over. I'm going to end this podcast and pick it up right again with transformations and then continue on with the next topic. This is my longest topic, and it's the graphing. But I don't want this podcast to get too long, so I'm going to end it right now. So see you